All right. In this lesson number 6, as part of this module, we're going to go ahead and talk about implementing roaming in a centralized architecture. In a centralized deployment model, which is essentially what we've been talking about this entire time, controllers can be placed essentially anywhere in the network, obviously. We need to make sure that we have the appropriate bandwidth and we have appropriate routing in place to be able to handle that. But you know, the location of the physical location of the controller is not always a huge concern. It is something you have to consider because we know that all the traffic from the wireless access points is going to get tunneled back to the controller using CapWAP unless we're using Flex Connect. But we try to centralize these controllers and maybe place them in a data center or in a location at our corporate office or whatever. It does require that the AP, that the wireless LAN controller tunnels are able to traverse the campus backbone network, and you have appropriate routing and enough bandwidth and so on. We can deploy controllers using iOS XE, but our focus has always been in this particular class and throughout these lessons has always been on the AirOS aspect. And now what we're going to talk about in this lesson is how do we facilitate roaming, moving from one access point to the next, whether it's on a single controller or multiple controllers in the AirOS deployment model. So we're going to talk about intra-controller roaming. We'll talk about inter-controller roaming. So intra meaning that all the APs are tied to a single wireless LAN controller. That's going to be probably a more common scenario for you guys. And inter-controller roaming, where we have access points that are associated to or connected to different wireless LAN controllers throughout the topology. We'll talk about mobility groups, mobility domains. We'll take a look at layer 2 dynamic roaming in this deployment model, and then we'll take a look at layer 3 dynamic roaming. Layer 2 roaming is a little bit easier to deal with because we're not having to deal with broadcast domains and VLANs and subnets. And then layer 3 dynamic roaming is a little bit more complex because we still have to maintain our presence in the IP space without having to disassociate the client and reassociate the client. So we'll talk about that. And then in this lesson, we're also going to talk about roaming with mobility anchors. And how a mobility anchor works. We talked a little bit about the concept of a mobility anchor when we were talking about guest wireless and how we could actually have the guest wireless traffic traverse the network and make its way over to the DMZ in an encapsulated format so that we're not sending or allowing them to connect their data traffic to our network internally anyway. All right? As a client moves from one AP to the other, there are many different messages that manage that activity, that roaming activity, so the client doesn't have to disassociate and reassociate, regardless of whether it's inter-controller roaming or intra-controller roaming. Even when a client roams from one AP, say for example in this diagram, the second AP from the left to the right, over to the third AP, from one controller to another, it's not affected and it's not going to actually kind of recognize that roaming event. I mean, as long as the SSIDs match, as long as we have the appropriate mobility group and mobility domain set up. That seamless roaming process means that we have to configure both controllers in the same mobility group and in the same mobility domain. And we'll talk about the difference between a mobility group and a mobility domain and identify what those specific differences are. All right. If the controllers are in a different mobility domain, then the client's going to have to reassociate and re-authenticate, so any active connections that client might have are going to be lost. Let's see. If a wireless client associates and authenticates to an access point. That access point controller maintains database information about that client. It creates this kind of active, real-time database about that client. Includes the MAC address of the client, the IP address, how it authenticated, its security profile, QoS properties, the wireless LAN, of course, that it's connected to, and it'll even identify the actual physical AP that it's connected to. The controller uses that information to essentially forward all the frames to the client and to manage all the traffic that's going to that particular client. Now, a controller can know controllers belong to different mobility groups. But just because they belong to a different mobility group, if there's knowledge about those other controllers, they're part of the same mobility domain. And in this particular diagram, we have a mobility domain that we've created and specified called the blue mobility domain. Roaming is not going to occur if the controllers are located in different mobility groups and do not know each other. Roaming will only occur if the controllers are in different mobility groups, but they're in the same mobility domain. So that's a very important concept that we have to understand, that we're dealing with devices that have to be in the same mobility domain. We'll take a look. We don't look at it in this chapter, but in a future chapter, we'll actually take a look at the process of configuring that mobility group and that mobility domain and so on. Okay? So how does the process work if I'm doing intra-controller roaming, meaning that I'm just moving from one AP to another within the same controller? If I'm moving from T1 to T2, which is what we're depicting here as an intra-controller roaming event, the client asks for re-authentication on the new AP. The authentication is done by a query that gets sent to the controller that the AP is actually connected to. If the controller is the same one, that the AP, like T1, T2 is the same, connected to the same controller that T1 is connected to, the controller just updates the database with the new AP information. Now, if necessary, new security contacts and new associations could be established, but not typically necessary. If we have the same SSID, we're providing services for the same VLAN. This is really just considered a roaming event, a layer 2 roaming event, and it's not really something that we have to concern ourselves with. With regard to, I guess I should say, moving from, say, one subnet to another, a layer 3 mobility roaming event. We'll talk about that one in a little bit here, okay? Inter-controller roaming. Now, there's a couple of ways that inter-controlling roaming occurs. It can either occur at layer 2 or it can occur at layer 3. Even though it may be a layer 2 roaming event, the process is different when a client roams from an AP that's joined to a single controller and then roams to an AP that's joined to a different controller. So let's say now we're moving from T2 to T3. When the client at T2 moves over to T3, it's going to associate to an AP that's part of that new controller. What happens is the client, what happens is during this move process, the new controller, being part of the mobility domain and the mobility group, exchanges mobility messages with the original controller. The client database entry that existed on the original controller then gets copied to the new controller. New security contexts, new associations get established if that's required, and then the client database entry gets added to the new AP or updated for the new AP's information on the secondary controller. All right, we will take a look at the actual steps piece by piece a little bit later on in this lesson. It's still a relatively transparent process to the user. The client sends a DHCP discover request. and session timeouts get exceeded. Those would be the only two scenarios. If the client for some reason decides that it needs to get a new IP address, or for some reason the roaming process takes too long, that's the only time that the client will ever know that anything has actually occurred during that roaming process. Now you can imagine that if I'm doing layer 3 roaming, inter-subnet roaming, that's a little bit more difficult, right? It's very similar to the inter-controller roaming process. The controllers exchange mobility messages once the client roams, but instead of moving the client database entry to the new controller, the original controller marks the client with an anchor entry and with a foreign entry on the new controller. We'll have a diagram that will describe this process, and I think seeing the diagram is going to make a little bit more sense than just kind of describing the process. But we'll take a look at that diagram a little bit later on. It's still a transparent process to the client, but the cool thing about this process is that the client maintains its original IP address, even if it's moving to a completely different subnet. That means I don't have to disassociate and reassociate and so on. In inter-subnet roaming, the wireless LAN on both the anchor and the foreign controllers have to have the same network access privileges. We can't do any things like source-based routing, source-based firewall components, because that will block that traffic that needs to go back to the anchor controller in this case. And we're passing essentially all the client's traffic from the foreign controller, which is the inter-controller roaming controller, back to the anchor controller. And so we'll take a look, like I said, at some of those details in this lesson with some nice pretty graphics, and that will hopefully provide a better understanding of the overall process. All right, so that's just kind of an introduction to the terms and the concepts. Mobility groups and domains, that's part of the mobility roaming process. It works, by the way, in the centralized environment. Also works in the converged access model when we're using iOS XE. But let's describe the difference between a mobility group and a mobility anchor. A mobility domain. We'll talk about mobility anchors as well a little bit later on. All right, but it's very important to understand the difference between a mobility group and a mobility domain. A mobility group is a collection of mobility controllers, what we call MCs, where roaming is configured and set up for the clients. It's a collection of controllers, and you cannot have any more than 24 controllers within a mobility group who share the same value that's configured as the mobility group name. So they know about each other in the process of communicating across the network and sending messages back and forth. They all discover each other as being part of the same mobility group based on the mobility group name, and they enter that information into something called a mobility list. The wireless LAN controllers then can dynamically share context, state of client devices, the loading information. We can also forward data traffic between them. It's going to enable that inter-controller wireless roaming. It even provides for wireless LAN controller redundancy, which is something that we had talked about previously. Actually, setting up the mobility group name is relatively simple, right? Let me pull up, if I still have it active here, pull up my controller configuration, and you can see here in this configuration we have a mobility domain name, an RF group name. So these are just names that we specify that allow us to identify the mobility configuration. And here we can specify the mobility group. Mobility group name is thinQtank. We can specify multicast addresses as well to identify essentially a way of communicating via a multicast. So what I would do in this particular case, if I wanted to add another controller to the same mobility group, click New, And then I just simply put in the IP address and the MAC address of the mobility group. And if I decide that I want to run a hash or install a hash, in this case, I could do that. So it's not an automatic discovery process, but it is a fairly simple process to manage in that you simply just add each controller, and you would have to do that on each of the controllers that you're trying to manage. Does that make sense? We'll take a look at the configuration in more detail, and you guys actually will have a lab that you'll go through to set that up as well. I'm not sure when that lab is going to take place, but at some point, you know, either this week or next week, you'll see that exercise. Okay? So that's how you configure that, but that's different. This group membership is different than the mobility domain. You can see here that there are some other configuration options that we have. So new mobility is when we're using the converged access scenario as opposed to the ArrowS process. We'll talk about that a little bit later on, and then the mobility anchor configuration, timer values, we'll talk about those. But all of this is done under the controller configuration screen. All right. The whole purpose of having this mobility group is so that the controllers can dynamically share context and state of client devices. The wireless LAN controller loads information. It can forward data traffic between the controllers. That's going to allow that inter-controller roaming process, and it provides for redundancy. All right. So lots and lots of reasons why you may want to implement this particular set of configurations. The easiest implementation, of course, is if you just have a single controller, right? If you just have a single controller, then it's a fairly simple configuration. You don't really have to worry about messages being sent back and forth between the different controllers and so on. We'll still talk about the different processes, but a little bit simpler. A mobility controller, which is part of this process as well, is responsible for caching something called the pairwise master key of all of the clients on the mobility controllers. That's what enables roaming of the clients within its subdomain and within the mobility group. Now, a wireless client can roam between any AP within the mobility group without having to re-authenticate to the network. If the AP being roamed to is not the same wireless LAN controller as the AP being roamed from, the client's security association gets transferred over to that new access point. These controllers, as you can see from the yellow lines on the diagram within the mobility group, are going to create a full mesh, and through that full mesh, that virtual mesh, they're going to exchange mobility messages, which is the status of the clients, and those get multicast to all the members in the mobility group. So you do want to specify in the configuration that you have, or you want to specify a specific multicast address. Make sure you don't use any multicast address in the 224 range, because those are reserved for well-known multicast functions. The multicast range that I typically use is 239 dot something, right? That's generally what most people will choose to an address. So I mean, it can be a completely random address from that point forward, as long as it's unique within the domain. Keep in mind, you may have to configure multicast in your network as well to support this particular process. All right, which from a switching perspective is not necessary. Switches generally just flood multicast traffic, but routers may have to be configured to support multicast for this mobility group process to work. All right, so they're going to form that full mesh and start exchanging all those mobility messages. A controller can only belong to one mobility group, and I just showed you kind of how we set all that up within the controller. At least I pointed you in the right direction where you can see that configuration. A mobility domain is a slightly different concept, right? You see here, mobility group is kind of a subdomain to an overall mobility domain. A wireless controller can know other wireless controllers that belong to different mobility groups. If that's the case, these controllers are said to be within the same mobility domain. Essentially, just a mobility domain is a collection of mobility controllers that we need to support mobility from. So maybe we have HQ1 on the East Coast, and we have HQ2 on the West Coast, and we have multiple controllers or even single controllers in those locations. We don't want to put them into a single mobility group because of the amount of messages and the exchange of information that occurs between those controllers, but we want them to participate in the same mobility domain. You can have up to 72 different mobility controllers in this particular case that can support different mobility groups. Within the mobility group, we're still limited to the 24 controllers within the group itself. For two controllers to be in the same mobility domain, they have to know about each other. That happens when the MAC address and the IP address of each controller are entered into the other controller's configuration. I showed you that in the configuration screen that I just went through. For two controllers to be in the same mobility domain, they have to know about each other. Let me show you where that configuration is. So if I go to controller and I go to general, we can see the default mobility domain name is listed here. And then you can also set up additional configurations under here. There's not a whole lot to change other than what's under the mobility group configuration, where we add, this is what we were talking about, adding the MAC address and the IP address of the other controllers. But you would still have to make sure that the mobility domain name is specified here as well. Okay? A wireless client can cross different mobility groups, but it still has to be within the same mobility domain. And as long as I'm staying within the same mobility domain, I'm not going to be required to re-authenticate to the network, establish different security associations within that particular mobility group. All right. So now that we've kind of introduced the terms and the concepts, let's kind of get into a deeper dive here and take a look at the process, the point of attachments, and the point of connectivity. You know, we talked about those identifiers a little bit earlier. Layer 2 roaming assumes that any wireless LAN controller that's involved in that roaming process would be layer 2 adjacent and share the same VLAN information, same SSID information as the original access point has, right? Whether it's on the same controller or whether it's on a different controller, any kind of layer 2 roaming event assumes that we're not changing subnets. We're not moving from one subnet to another. So we share the SSIDs. Those SSIDs are mapped to the same VLAN, the same subnet, and so on. Incidentally, the controllers in this case have to have the same AROS code in order to support this roaming process as well. Layer 2 roaming can be intra-controller, so moving from one AP to another within the same controller where the client's POP and POA remain the same. Layer 2 roaming could also be inter-controller, where the client's POP and POA would move from one wireless LAN controller to the other. That's the flow that we're going to look at here. You can see there are different controllers here. And so we're moving from one controller to the other. In this case, what we see listed on the diagram, it's assumed that the client's going to stay in the same subnet, so no layer 3 activity is going to be required here. All right. In centralized deployments, the controller is both a mobility controller and a mobility anchor. And we defined in a previous lesson, if you're just watching this lesson, go back to one of the previous lessons to see what the definition of that mobility controller and mobility anchor is. So here's the steps, right? Initially, what's going to happen is the user's point of presence and point of access are co-located on the same controller. The user roams to a different AP. It gets associated to that controller. All right. Now, you can see the yellow lines kind of indicate the data path of the traffic, the CAPWAP tunnel configuration, the intercontroller tunnel that occurs, and then the wireless client traffic. Notice that, well, the easiest one to understand, of course, is the intercontroller traffic, right? We have this link and this communication path that's occurring via a CAPWAP tunnel, by the way, to communicate data from one controller to the other. Now, the bottom controller in this case was the original controller that that I had associated to. That's where my point of presence and point of access is. Okay, and you can see that we have a CAPWAP tunnel. All my 802.11 control traffic and my data plane traffic goes to that controller. All right, and there's a CAPWAP tunnel that exists on the other AP as well, right? So this is just kind of our initial association, right? Everything makes sense. We've got the back-end communication between the controllers. I've got my CAPWAP tunnel that's going from both APs to their respective controllers in this particular case, and my client's data traffic goes from the AP, the primary AP, to the primary controller, and then it goes out of the de-encapsulated traffic, leaves that controller and goes out to the campus. Now let's talk about what happens when I roam to the other controller. All right. The new controller exchanges mobility messages with the original controller, and the client database entry then gets moved to that new controller that's in the same mobility group. So my point of presence and my point of access moves over to that new controller. Okay? New security contexts and associations may have to be reestablished here, but usually that's transparent to the user. The client database entry that was originally created on the original controller gets copied and updated for the new AP on the secondary controller. Well, we'll call it the foreign controller in this case, even though that's a term that we typically reserve for layer 3 roaming. The client's entire mobility context gets moved. All right, that's what that POP and POA represents, is the mobility context of the client itself. The client's traffic also moves to that new path. All right. Now you'll notice here that the diagram indicates that if we go back to the previous diagram, the green line indicates the traffic flow to the controller. The blue line represents the de-encapsulated over the CAPWAP tunnel, and the blue line represents the de-encapsulated traffic that's going to the campus. If you look here, the green line represents the data that's passing to the controller, and then the blue line represents the data that's being de-encapsulated. All right? Now, you'll look at that and you go, well, wait a minute. How is that possible? That AP is not associated to that controller. And the AP doesn't have a CAPWAP tunnel to that other controller. It's kind of a pain in the butt, guys, but the diagram's not right. All right? That green line should be represented as going up through the CAPWAP tunnel to the new controller. Obviously, we can't get from one CAPWAP tunnel to another CAPWAP tunnel. With this AP would have had to have had a CAPWAP tunnel established with this controller in order for this data flow to occur. So the diagram is not really accurate. All right. Everything that's happening here is going to be completely transparent, assuming that the roaming process was smooth. We didn't have any timeouts. There was no DHCP discover issued for lack of connectivity or whatever. All right. I wish they would have had the correct information in the diagram. That would be helpful, but well, we deal with it. All right. In this diagram, the two controllers don't share a common set of back-end VLANs. They're sharing the same SSIDs, but those SSIDs in this particular case are mapped to different VLANs and different subnets. Because the distribution switches that the controllers are attached to are routed instead of switched, the traffic doesn't flow across the same forwarding VLANs. So we can't do a layer 2 roaming, we can't facilitate a layer 2 roaming process in this particular case. Because that new wireless LAN controller doesn't share the same subnet information, the client without mobility would essentially lose their IP address, and then they would have to go through the DHCP process. They would have to go through the whole reassociation and reauthentication process after that as well. But thankfully, because we have inter-controller layer 3 roaming, that's not something we have to concern ourselves with. It requires that the client's POP gets anchored to the original controller, and the POA moves to the foreign controller. All right. If you recall, lost my train of thought there. If you can recall, the POP is what we call the point of presence, right? That's the physical location where that client was originally located. The POA is the point of attachment, or I call it point of access, but it's really technically called the point of attachment. So when we're talking about these terms, I want to make sure you understand the difference between that point of presence and point of attachment. All right. So if the client associates to an AP, so let's say in this diagram here, it associated to the AP on the left, the controller that it's associated with that particular AP places an entry for that client in its database with all the information that we talked about on the previous slide. Includes MAC address, IP address, QoS, VLAN information, etc. The controller uses that information to forward frames and manage traffic to and from that wireless client. And the POP and the POA are located on that particular controller. All right? Co-located, I should say, on the same controller. Now, what happens when the user roams from the AP and its associated controller, which in this case is called the anchor controller, to another AP and its associated controller, which is the controller on the right side, and in this case, we would call that controller the foreign controller. So my original point of presence, my original point of attachment is going to be the anchor controller. In layer 3 inter-controller roaming, we're going to call that the foreign controller. All right? Well, this is what it looks like. And in this particular case, the diagram is actually correct, and that's good. Okay? So the new controller exchanges mobility messages with the original controller. It sees this new attachment, by the way. It sees a client moving in and attaching to the network. So that triggers that set of messages being sent to all the different controllers, basically saying, hey, I've got this guy that's trying to connect to me. What do I do? Here's his information, by the way. Does anybody have any information relevant to this particular individual that I can use to change the security association and make sure that this client can still communicate? So that goes to all the other controllers in the mobility domain or the mobility group, and then the database entry gets copied to the new controller as long as they're in the same mobility group. That new security context allows the client information to get updated for that new access point. The client's point of attachment gets moved to the new controller. the foreign controller. The client's point of presence still stays fixed on the original controller, which is called the anchor controller. So POP stays on the left, POA moves to the right. This is done to make sure that the user can maintain the same IP address information across a layer 3 routed boundary. And it's also very important to ensure that we have continuity of policy applications, right? We have policies that we apply to the wireless LAN. Those policies might have access lists, might have, well, any kind of policy that we can create for that particular user. We want to make sure that that policy information stays the same. So the client's traffic then gets tunneled back to the original anchor controller, and we call this symmetric mobility tunneling. Okay? So we're actually tunneling that traffic back to the original controller. That communication is occurring over this dark green link. That's the CAPWAP tunnel between the foreign controller and the anchor controller. So even though the client may be attached to a VLAN that's in a different subnet for the same SSID, because that traffic is encapsulated back to the controller, that then gets encapsulated back to the anchor controller. From the foreign controller, we can maintain our subnet information. Okay? All right. Hopefully that makes sense. All of this stuff is pretty much automated. Well, it is automated once you've established the domain, the group, and you've added all the different controllers to the same mobility group. Everything is kind of handled internally by the controllers themselves. We can also use something called auto anchor mobility. Typically, this is something that you would use with guest access. I talked about this briefly when we were talking about mobility in a previous lesson. We want to make sure that the guest traffic that's typically just going to the internet doesn't enter the corporate network, right? It's going to be routed over the corporate network through an encrypted tunnel, but we're going to pass the traffic through the corporate firewall, at least the unencrypted traffic through the corporate firewall, so that we can maintain adequate security policies for the traffic flows that the client is utilizing. To implement a geographic access policy, we need to have this guest anchor configuration, right? Geographic guest policy or access policy means that regardless of where you're attached to in the corporate domain, you're going to have a consistent policy when you go to the internet. All right. So let's say a wireless client associates to the AP on controller 1 on the left on the guest SSID. The guest's point of attachment will be controller 1 where they associated. The controller 1, because of this auto anchor configuration, is going to point that client's information or that client's traffic to the guest anchor for the guest SSID. All of the guest user traffic then gets tunneled from the mobility anchor to the guest anchor by the firewall, right? This is a symmetric tunnel. We're going to be using CAPWAP or other methods to communicate that traffic, typically CAPWAP. The guest user's IP will come from the guest anchor itself. That's part of the whole login process, whether you're doing WebAuth or open authentication, causing them to establish their own accept the user acceptance, user access policies and whatnot. And then the anchor controller will provide addresses to the guest. The guest anchor becomes the point of presence, and the guest will stay static at that point of presence. It doesn't matter if they move from controller 1 to controller 2 to controller 3. They're always going to have their traffic sent back to the guest anchor controller. The guest, once they're authenticated, probably using WebAuth, they're going to have all their traffic de-encapsulated at the anchor controller where they move out of the network through the firewall and so on. So what happens if the guest roams through the network? Well, it's a simple process, right? The client roams from an AP attached to controller 1 to an AP attached to controller 2. The guest's point of attachment is now with controller 2. That database information is being exchanged between controller 1 and controller 2, just like we saw with regular layer 3 mobility roaming and layer 2 mobility roaming. The guest's point of presence is still attached to the guest anchor. And then the guest user's traffic gets tunneled from wireless LAN controller 2 to the anchor controller. Since the guest user is anchored to the guest anchor controller, the authentication, the IP addressing is sourced from that location. That never really changes. So the guest's IP is not going to change. Their point of presence doesn't change, regardless of where they go within the corporate network. It's a very typical way of establishing guest access. All right. So we were just introducing a lot of the concepts of this, a lot of the concepts of mobility in this particular case. If you guys end up configuring mobility, I did kind of demonstrate the different areas where you can configure that those settings. And later on, we'll go into a more in-depth discussion about the actual physical configuration. But we talked about wireless roaming between APs, using intra-controller roaming. We talked about how it works with inter-controller roaming and how information is exchanged from one controller to the next. We talked about the difference between layer 2 roaming and layer 3 roaming. Layer 2 roaming doesn't have a concept of anchor controller and foreign controller, but layer 3 does. We talked about layer 2 roaming and how that can be intra or inter-controller. Both are relatively easy to manage. Mobility groups are a collection of mobility controllers for layer 2 and layer 3 roaming. By the way, mobility groups are also used for radio resource management, being able to collect information from all the access points in the domain so that we can do spectrum analysis and manage that spectrum. Mobility domains contain one or more mobility groups. We talked about that. A mobility group can only contain up to 24 controllers, whereas a mobility domain can contain up to 72 controllers. All right. What else are we talking about? We talked about the point of presence or the point of attachment. They stay fixed in a layer 2 intra-controller roaming process. Makes sense because we're not leaving the controller in this case. Both the point of presence and point of attachment move whenever there's a layer 2 inter-controller roaming event. Layer 3 roaming is intra-controller roaming. The POP stays fixed on the layer 3 inter-controller roaming, and the point of attachment moves to wherever the wireless client is attached to the network. We talked about auto anchor mobility for guest access and how the client's point of attachment moves with them in inter-controller roaming events. All right, so that concludes that lesson. That also concludes this module. So we're going to now move on to the next module, and we're going to get even further in detail into a lot of the different things that we've been talking about, right? We're kind of moving through these lessons, introducing piece by piece and identifying additional components. But now we're really going to get into the meat of it, right? The actual implementation of converged wireless access. That's what Module 5 is all about. Configuring client access, implementing roaming and the converged architecture, initializing the entire environment, essentially. So we're going to move on to that. We'll see you in the next lesson.